Yeah, I think they were lethal.
We still have a couple minutes. Oh, really? Yeah, so let's start like a wave. Cheering. The vendors, the developers, the late, behind the curve. In order to change the arms race, to shift the costs of attack to the other side, or people or money, we need to change the way that we play this game. And I think that this work that David Giametta and Andrew Potter are doing is vitally important to shifting this, the cost of things, to how the arms race is played. And I really look forward to hearing them talk about it. So may I introduce David Giametta and Andrew Potter.
I'm Andrew Potter of the Giametta Potter team up here. So,
You just hit.
yeah, got it. Okay. So, what we've been doing for the past 2 or 3 years or so is we've been trying to deal with the question of what do you do if you've got millions of pieces of malware and you want to know, well, what is it that you've got? We started out with only a couple of dozen pieces of malware to work with, and that made it tough, but over time we were able to increase that, and so now we've got a little over 2 million to work with, plus a sizable collection of non-malware. The work we're going to present today is a piece of a larger set of experiments with. We've been trying to figure out, okay, if you've got all of this stuff, can you organize it into manageable, meaningful groups or clusters? Can you do risk assessment of it? Which stuff is the stuff that really is malware? What's not? How do you know that? The spatial analysis, which is where we're focusing today, is a statistical and visualization technique for looking at smaller groups once you've boiled them down and getting a feel for the shared structures within them. We also have been working with what we were calling lineage trees, which is to try to tease out the inherited properties within a cluster of malware artifacts. And we're also conducting a set of components. All of this is just working from the binaries. We started out thinking, well, we need to disassemble everything and then run our analysis on the disassembled code so we can study the instruction sets and do scalable reverse engineering. And somewhere along the way, somebody said, well, why don't we just try a little experiment taking a different approach. We'll just look at the file, or perhaps sections of the file, like the code section or the data section that has numbers between 0 and 255. And we'll start doing statistical studies on those numbers without really looking at the more anthropocentric view of how we as humans like to read code. So we did that first with just some clustering experiments, and we found that if we combined that with other types of techniques, feature extraction, we could get pretty good clusters out of it. And once we realized that, then we were sort of off and running down this path where we are applying the similar techniques on all fronts of what we've been doing. So what we've been using is a number of clustering techniques and machine learning techniques to try to accomplish our goals. So I guess I kind of got ahead of myself on the slides here, but usually when I present, all I really need is the title slide anyway. So what we're trying to do, given the scale of what we want to do, is to do these very quickly. Our basic clustering algorithms right now will run at process about 100,000, depending on the size and whatnot, files per hour, which means we can go through several million pretty quickly. One of the things we want to focus on is this idea of variance. One of the things that trips up our current analytical capabilities is the malware writers can make subtle variants in their code, or they can write polymorphic code that'll make the variance on its own, which if you're using signature type detections can easily trip you up and you can fail to detect things. So while we're not trying to write an antivirus tool here, what we are trying to do is have efficient ways of grouping variants into coherent sets so that we can take a look at them and do further studies, such as the component. You've probably seen charts like this that tell you, yeah, there's a lot of malware out there and it's getting a lot worse. And in this case, in this chart, actually the chart it's worse than what the chart says, because the column on 2013 out to the right was taken, and so it doesn't have the full year's data in it. So I'm about to start talking for some of the slides David's going to present, so I guess I'd better stop and hand it off to him. He's going to present the nitty-gritty of a set of experiments that we've been doing using the Mandiant data sets that gained a lot of notoriety earlier this year. He's done a whole lot of experiments there on a whole lot of sets. He's going to go into detail on one of those.
So, as Andrew said, I'm David Giametta, and I like science, I like experiments, and I like malware. So, I want to go back real quick to the last slide. So, like you said, it's even worse than we thought. In 2011, variance to family ratio was 5-to-1. In 2012, it was 38-to-1. And this year, the numbers haven't come in, but you can see the trend. It's not looking good. So I really hate wasting time looking at just another variant of a piece of malware that I saw last week. So this kind of helps. So our dad can't kill them with kindness. The problem doesn't end. I continuously get more malware. I continuously have a bigger database. I continuously don't know what I have. It's a real big problem. If we could change that dynamic, if we could make it harder for them to create successful malware, if we could make it easier for us to gather information, to know this is something I saw last week, I'm not worried about it, that would be really, really powerful. So quick, it's analysis. Static analysis, dynamic analysis. I'm sorry if your favorite tool's not up there, mine are. It takes forever. It gives us a really great picture of the malware. It just takes too long. Can't keep up. So no spatial analysis. Spatial analysis, and you'll have to forgive me, I have a lot on this slide. So spatial analysis is the idea that you can take byte sequences characterized by statistical features. And I'm going to introduce the term keys. We call those keys because we encode them into one number. And we graph them into 2D grids where new exploitable information is obtained. This exploitable information is the structural similarity that you see. So I'm going to actually tell you what this picture is. This is an embodiment of spatial analysis. This is the output from a tool document. On the left, in the left pane, that's actually a 9 million by 9 million grid. And I'll take the statistics we use because I really hate people that go all high level. We're actually using mean and sigma, so we break them into byte windows. We break into byte sequences and do them running mean and sigma. And then we plot this. We plot this, the max mean and max min mean and max sigma and min sigma on the left there. So what you're seeing is the red malware, the green is another piece of malware, and the yellow is where they overlap. So we're actually adding stacking. So when these sigmas, means and sigmas fall into these cells, they are stacked, and we can tell where they match each other. That's the left pane. The right pane is actually a 0-2 size representation of the bytes in yellow. Again, the green and red are the pieces of malware. So, a little analogy, and so many people have told me, you spelled variance wrong. Yes, I did variance wrong on purpose. So, actually, all of us have heard of n-grams. It fails miserably, and there's a reason. It can't look past small differences like that. But spell checkers do it all the time. And the way they do it is they look at mean. One of the ways they do it is they look at the mean and the misspelling of variance. And for those who don't know, 22 is the V in the alphabet. 1 is the letter A in the alphabet. Continue on down. They both equal 13 for the mean. That's really awesome. So imagine 2 pieces of malware packed, or perhaps 1 piece of malware unpacked and a variant of it packed. Small differences in these byte windows that we're looking at. So I want to show the structure again, and I want to explain it a little bit better. So new exploitable information is the spatial structure. So I showed you on the left where they start to align. The previous example that I showed you was 2 pieces of malware that we were red and green to help identify them. But at this point, we're looking at families. We're looking at multiple pieces, so we just show them in gray. The top one that you'll see right here is actually 2 pieces of malware with nearly identical structure. So where the actual byte sequences are matching, where these keys are matching, that's what I'm showing there in yellow. So below that, I'm showing 16 members with 2 families. So, and I'm sorry that they're not delineated like the top one. You'll have to take my word for it. This is 16 members with 2 distinguishable spatial structures. So it's not just that they match byte sequence. They have matching keys or these characteristics of byte sequences. It's that they share structure. And that's actually 2 different families from the Mandiant family, from the Mandiant APT1 report. So if you don't know why this is cool already, shame on you. Computers can perform statistics on byte windows really, really fast. Kung Fu strong. Humans can easily and accurately identify patterns. Pretty pictures. So this gives us the ability to quickly identify families and variants and get a better understanding of what malware we're seeing, what malware we have. So when I first was introduced to this, I was just handed the tool, told about this spatial analysis, and I really doubted it. I doubted it so much that I didn't do what I was supposed to do, to analyze the Mandiant set, and I ignored it. I actually instead analyzed my resumes because I didn't want to do that. My friends and my resumes. So I had 5 versions of my resume, of my friends' random resumes. And these all have similar formats, right? Work experience. We all went to the same school. We all went to Mississippi State. We all worked at the same company back in the day. We were all about the same age. We were all from the same city. So really similar information. I wanted to see if it could even tell the variance of my actual resume. And it did. And that was pretty impressive. But I was still pretty much thinking that can't be. And these are the reasons. I mean, so you're telling me that we're going to take statistics of byte windows and then encode those statistics. So we're not even looking at the statistics of the byte sequences. And I thought, that sounds kind of crazy. Packers have options. I mean, UPX, faster and better. They all do it. So those were my big 2 concerns. Other people raised other concerns. Malware behavior can be reached through many means, many different pieces of code. I think there's 3 off the top of my head ways I could think of making a keylogger. So how do you do that? How do you tell the difference? So also someone said, well, what if I had multiple pieces of malware packed by the same packer? Would it identify them as being related? and keying off the packer instead of the actual malware. So I really love when we do demos and these kind of things, and so that's what we're going to do today. Today, I want to look at the Mandiant APT1 Yahoo family. I needed families that had a lot of information on them and looked really pretty in front of an audience, and so I picked this one. And I'll be testing, we'll test the null hypothesis. We'll try and disprove BAT. We'll try and disprove spatial analysis by examining the tool, by examining the results of a tool built on it with a traditional tool, pbrowse, and we will look at the information and also the information provided by Mandiant and what they say about the family. So a new tool appears. This is the visualizations I've been showing you so far. They come from this tool. This is byte assessment tool because we're really awesome at naming things in this field. And yeah, let's dive in. Walkthrough. So what I'm actually going to show you, so I'll talk about it before I show you. We'll start by examining the matching byte areas and non-matching byte areas with telling us exist with pbrowse. Next, I want to actually take a look at the family and see if that family, compare those results with Mandiant and see if those are equivalent. Then finally, I want to show you a new thing that I actually helped do, where we export a detector to find any other related malware in our malware collection. So demo, there we go. So I have BAT pulled up here right now, and in the middle I have the Mandiant family in my in class, and I don't know if I can, I'll attempt to, yes, in my in class right here. It's 11 pieces of malware. I'll tell you a little bit about them. They actually, every 10 minutes, I think it is, or every 10 seconds, they try to go to a URL, an encoded URL, and get you to download some, and it's really hilarious. So let's take a look. AA41F and CC3A9. I'm going to initialize on these two, and we'll see what happens. So AAA4F1 is in green, and CC3A9 is in red. So I did a min-max to min-max that grid on the left, and then I'm plotting it now. So, aha, pattern that I showed you before. Very good at seeing patterns. So this is actually exactly the one I showed you before. And this is spatial analysis via BAT's initial claim, right? It's saying that, aha, I found areas where there's matching byte sequences. Well, when I finally did decide to go ahead and start looking at this, the first thing I did was, well, let's go see if that's true. And that's what I want to do today. So I actually have these two pulled up right here now. And let's take a look. So on the left, I have AA4, and on the right, I have CC3A. So let's take a look. As you can see, they're actually the first line, and I don't know if y'all can read it as well as I can, but the first line is exactly the same. The second line, there looks to be a compiler artifact, which is an ampersand, right before the get module handle. And on the next line, there's a P, which looks to be also maybe a compiler artifact left. And on the right, those don't exist. But other than that, these two are identical. And that's kind of the power of looking at statistics, and it relates back to my spell checker. We can look past these small differences. So they're identical, and that's exciting, but it's not enough, right? You actually have to say, well, let's look at the non-matching areas and see if those also don't match. So let's do it. Oh, I forgot to show you the intermediate step. I actually write in this tool, all the offsets of matching byte sequences are written off. And I was looking at this biggest block right here, and I'll pull that up so you guys don't think I'm crazy. And you might think I'm crazy anyway. So we were looking at 2541, which is where that matching area started right here. Let's look at the non-matching area. So one of the non-matching areas is 3888, which in hex is F30. Off the top of my head, ladies and gentlemen. So let's scroll down and see. So I've got F30 pulled up right here. Let's go over to the other side and do it the same. So this is an area supposedly of non-matching. But let's put it to the test. It looks like the first few lines actually do match. Until you get to this third line. And I'll read it out to you guys. On the left, it's HTTP. It's an encoded a website, an HTTP URL. It's http://eads.ruck.org. And on the right, in the other sample, it's http://mediazonet.us. So that's, and it goes on for a couple more lines. I didn't read the whole thing, but that's a pretty big difference in these two. Let's keep going though. So again, in the left, if you go down to FA0, right around here, this one, it's http://drilquip.delta. And on the right, it's http://news.imly.org. So two totally different websites in each, and that actually ups the ante. I'm really excited to find this out. That means that the tool I'm looking at is not crap, at least for now, right? More experiments, always more proofs. But that was really exciting for me because I realized that does work. And the statistics, the mean and sigma of a byte encoded can tell us something. So next, I want to run this entire family. Now, for this tool, what this tool is doing is it's found, and it's trying to find them in all the members of this family. And they should all be there because they're related. That's what Mandiant told us about the Yahoo family, that they're all related. Even though they put in a catch there saying that maybe not all the members of every family share behaviors. But they did tell us that these are Yahoo. So let's take a look. On the left of each file, it's going to tell us how many keys it found. And I didn't start off by telling you guys, but originally there was 519. And so we go down and we slowly see that our number was 496 and went to 378. And then in these last three samples, it's nothing. They don't exist. So I'm in an intermediate step. I'm trying to build a solid family. So let's take those out, and we'll put them back in later. Let's rerun this, and then we'll plot it, and we'll see what happens. Again, I'm looking for this. I'm looking for the structure. I want that structure to be there. If this is a true family, I want a structure that goes down throughout each piece. So that's a great question. You asked keys that I found. It's not just minimum number of keys. So actually, I'll begin to plot this and I'll answer your question. Right here I have the byte. I can actually change the byte window size, how many byte sequences I have. So that also plays a factor into that. So if I make it smaller, my key is much bigger. I have many more keys. So a lot of research has gone into that question, and it's still not quite answered yet. It's finished, and I appreciate that question, by the way. So let's see if it's plotted. Hopefully it's plotted. No, it does not want to plot for me. Let me go see if it's actually done. I have the file open that it's trying to write to. Yay! Well, I caught it, so that's pretty good. So here we go. It's asking me if I wanted to save it, and I don't. That was really useful at the time we were developing this. So check it out. There's this big middle line that was here, and it exists in every one of these files. Well, I really want to go back and look at those three that Mandiant said were also part of this family and see if that structure is there or not. And that's a pretty clean structure. They get pretty dirty. This one I chose because it's really nice for an audience. Let's take a look and see. So I took out these top two and this bottom one, I believe. Yes, I did. So let's take all of our keys that we use these last three and see if they exist or not. Should only take a second. Maybe a few seconds. Oh yeah, I'm sorry. So this is actually the next part I'm going to show you takes out all this slowness, and it's the really, really exciting part. So let's take a look. Indeed, these keys, this structure is not present at all in these last three. And again, I'm sorry they're not delineated between samples. So what does that mean? It turns out that these three don't have shared bytes. Perhaps they have a shared behavior, and the way Mandiant said they did their analysis, it was on behavior and strings. So perhaps they shared some strings, a few strings, perhaps they shared some behavior, but they don't share bytes, and they don't share the byte structure that we're seeing here among all the other ones in that family. So this is the bread and butter. This is what I've been working on. Let's take these keys and actually get proactive. So this tool, it took a few minutes for us to look at this family, and we already excluded a few from the original family. Let's see if we can find new members. I really would like that, because that would help with our initial problem. So let's export a file. And I've already exported one, so I'm going to cancel that. So I'm going to run this, and what I'm feeding in, this is just another Python script. What I'm feeding into this is how I want the offsets, which is 0, the step size, which is 200. So that's how many steps it takes into the bytes before it takes a byte window and does the statistics on it. And then if I want to do the full file, or if I just want to wait till I get that first hit, that first key that makes sense, that's found, and I'm going to store them, and I'm going to store them in the hits, and I'm going to go through. I'm going to go through my own personal malware collection. This is about 1,000. I'm going to run it. This is about 1,300 pieces of malware, just the ones I really like. No, there was no extraction through virtualization. This is straight from the bytes. The gentleman asked if I was using if I was getting my statistics from a virtualization or from the byte. Okay, straight from the bytes. No, I'm not doing anything like that at all, actually. I'm only specifically looking at the binaries.
static.
It's completely static, yes. And I'll let that run, and I already have the results, so let's take a look real quick. This is my hits folder. I ran this earlier, so I didn't have to take my entire time and give you guys time for even more questions, perhaps. And in here, it's very, very interesting that it found a couple that weren't there before. It found 1C16 and D169. It also found a third one, but I'm not including that because I can't. This is a prototype tool, and I actually can't display it. It's so large. As I said before, it's not just about shared keys. It's about the spatial structure of these keys. So I want to actually take those two that we talked about just now and analyze them and see if they do indeed share the same structure. So let's pull these over and take a look. And let's take out those previous three that we don't like anymore. So I'm going to redo my scatter and replot these. And it'll take a few seconds. But I want you guys to keep an eye on this over here as it's processing through my personal malware set. I think it should finish in about 8 minutes, and that's 8 minutes for 1,300 pieces of varying size, including some documents which apparently I left in there. Yeah, that was an accident. But it doesn't care, right? And that's actually kind of cool too, and that's how I started the talk, was that I went through my resumes. It doesn't matter. So take a look. Actually, these two pieces that this classifier, or this detector, I should say detector, because it doesn't provide traditional percentages of accuracy. It just tells me if it found the hit.
When you're analyzing this malware, how do you know where to start? Because you're going to be
An excellent question.
in the middle of a
Yeah. So when I started looking at the Mandiant set, I went by size. And you can see on the left here that this is actually the size, and I could sort by size. And I started looking at ones that I thought would be relatively the same size. So I was actually artificially delimiting this process. But as I've grown through this process, I started thinking, well, why don't I just look at ones that I think are two that are related, and then export a detector and just go find more, and then build that up. And that's actually been really, really, really useful. But I started by delimiting, by looking just at the size.
So you always use an offset of 0, and rather than, within the packet stream, you start with the.
I'm sorry. What's?
You're doing the entire packets. You're doing the entire file size. You're not doing an offset.
So you're asking some really advanced questions. He's asking, why aren't I starting at an offset? Is that correct? That is actually in this version that we're showing today. I don't have that, but in the version that's actually developed, that's being developed right now, we are finishing that. So this detector no longer starts at the beginning of the file. Why would we start at the beginning of the file when we're looking for this structure right here? Why not just jump to where I think it might be? And that's exactly what we started doing now with the detector. I want to show you those results real quick before I jump to the next question. So they did share the same structure. Those two that we found with the detector shared the same structure. So that's really, really cool that I could just export a detector, and I could initialize this off of just two members. And I can literally say, I think these two are related. I've already analyzed them with IDA. I've already analyzed them with pbrowse, whatever. I think they're related. Why don't I go look and see if I can find any more members of this. And if you can imagine for a moment that you string these detectors together, it becomes really, really, really cool. And that's exactly what we've done to go through our 2 million database. And what was even more amazing was that during this process, we found pieces of, hold on one sec, I will come back to you. We actually found pieces of APT1 in our own database of 2 million. And we weren't working with that. We were just working with APT1 to see what we had. Yes, sir.
Have you considered offloading some of your data processing to like a Hadoop node for larger library sets?
So repeat that one more time.
Have you thought about putting most of your processing into a Hadoop cluster for your larger sample sets?
Yes, yes. Have we considered off-siting our processing to like the cloud or a cluster, something else, a server of some type? Yes, yes. Yes, we have. And it gets faster. It just continuously gets faster. So that's one that we're considering doing as a next step. We haven't done it yet. And that's what I'm actually encouraging the team who originally developed this to do. I only worked on the detector, which was really fun for me, after I was convinced that it actually worked. But yes, that is what we're planning on doing next to speed up the process. So actually, it should be done in a moment, but I want to go back to my... So spatial analysis is the ultimate weapon.
Well, before you finish conclusion, since we only have one microphone, or the tabletop microphones, if you're interested in asking questions so that everyone else can hear, could you come up and line up to use the mic?
Yes, yes. So spatial analysis is the ultimate weapon. No, okay, it's not, but... and I should have said ultimate weapon, by the way, for all of my friends out there, Final Fantasy VII. It's really, really good at getting a better understanding of what we have. And that's really, really important if we want to look at only unique pieces. And that would help flip the dynamic. So yeah, reduce the amount of malware that must be reverse engineered. That's the point. That's what we're trying to do. Understand what we have. I want to give some shout outs. Oh, I didn't blow it up. Someone could have warned me. My wife's awesome. Yes. Dr. Holger M. Janstich was the concept creator for spatial analysis and the lead director in BAT development. So Jamie Hanley was a main developer. Andrew Potter, I'd like to thank him for coming up and doing this with me. My friend Wesley McGrew, who helped me review my paper. My friends and family at Centaur, my peeps, and the ShmooCon. ShmooCon, you guys for showing up, and the ShmooCon team for being really, really cool. Thanks, guys. I would take questions. Any other questions? Please come up. I like you, actually.
I was trouble on another project.
I like questions, and that's
Hello?
how I started this process, actually, was by questioning.
So it occurs to me that the actual compilers, the versions of the compilers in the libraries are actually the indicators that you're identifying.
Yes.
So
yes.
have you actually reverse engineered the identification of the compilers in the libraries? Sorry, I'm being forced to eat this. This is very funny. To actually reverse engineer to then do the pattern analysis on which tools are actually being used.
So we have done that research, and it's not in my official paper because I had to limit that down to 1,000 words. But I can provide you with that information afterwards. I might have it on this machine here. We did several rounds of looking in to see if we're actually keying off the libraries, because we didn't want to key off the libraries. We didn't want to key off common libraries, and that was actually, that I should have wrote that into the doubts. That was a doubt proposed by the team as well, that it would be useless.
Have you actually run a data set or a group of data sets across variable offsets so that you can build up families based on, because it looks like the attack vector right now that I would use against your product
Yes.
would actually be variable buffering
Yes.
of offset bytes. Therefore, you can actually provide from a statistical attack model.
Absolutely, absolutely. So what we did after this is I ran through the entire Mandiant data set, Mandiant APT1 data set, And that was very common. In the variants, they would put crap at the beginning, crap in the middle, crap at the end, just to try and fool it. And I actually did that experiment in my paper that is submitted, where I took that and I decided, well, how far do I have to break this up? And it becomes to the point where it's no longer a variant that I would cut with the word being defined as minor changes or repacking or renaming.
From watching the malware developers, they typically pull that from a standard pattern
Absolutely,
tool
yeah.
or randomness. That actually is another key identifier. Have you considered using that? The randomness, the crap that's actually installed in there, it's either pulled from
No, I haven't,
one
no.
of three components, and different programmers actually use those particular techniques.
Are
and
you talking about like a malware kit?
Yes.
Yes. We played around with GVDG5
Okay.
to create many pieces of preset malware that would do exactly that, yeah.
Okay.
Very cool stuff. Thank you for
Thank
those
you.
questions, by the way. And if you want more information on that specific research, we could exchange contact information. Yes. All right, any more questions? Oh, yes, sir. Gentlemen.
Yeah, as far as the statistics and analysis, it seems extremely close to me to bioinformatics and analyzing DNA.
This man just earned a star. So this entire technique was borrowed from bioinformatics. Yes, you're correct.
I was curious what literature, bioinformatics literature, you'd read through for
So
developing this.
they are referenced in my paper, but Dr. Holger Janicic has actually published many papers on bioinformatics and how this technique is directly derived from that. Yeah, so for you guys who aren't in the loop, I'll show you real quick since we have the time. Imagine for a moment that that's DNA and you're stacking different pieces from different families, and you're looking to see if they share the markers, if the markers are highlighted at the same spots. Very cool stuff.
It occurs to me there's another use for this tool, which that it might be a good de-anonymizer. You might be able to run a whole bunch of written text against it and determine who wrote it.
That would be very cool. Anybody else have suggestions? Because that's how I actually came to this. Was I didn't believe it, wanted to disprove it, and then tried.
Is that available?
Talk to me afterwards. I'm not in control of that process. Andrew. Anything else? All right, well, thank you guys. Oh, wait. Yes, sir. Gentlemen.
Oh, yes. So this is really cool. I am doing some e-crime stuff, and I'm thinking I can use these techniques to further the variance of being able to tell, is this a bot, is it not, and find similarities between big groups of malicious users. We see groups of 2,000 at a time. How do you pick out the good versus the bad? And so thank you. This is really cool.
Absolutely, man. I'll exchange contact information with us. Absolutely. Thank you, guys. Thank you.
Just a sizable collection of non-malware. The work we're going to present today is a piece of a larger set of experiments with. We've been trying to figure out, okay, if you've got all of this stuff, can you organize it into manageable, meaningful groups or clusters? Can you do risk assessment of it? Which stuff is the stuff that really is malware? What's not? How do you know that? The spatial analysis, which is where we're focusing today, is a statistical and visualization technique for looking at smaller groups once you've boiled them down and getting a feel for the shared structures within them. We also have been working with what we were calling lineage trees, which is to try to tease out the inherited properties within a cluster of malware artifacts. And we're also conducting a set of components techniques on all fronts of what we've been doing. So what we've been using is a number of clustering techniques and machine learning techniques to try to accomplish our goals. So I guess I kind of got ahead of myself on the slides here, but usually when I present, all I really need is the title slide anyway. So what we're trying to do, given the scale of what we want to do, is to do these very quickly. Our basic clustering algorithms right now will run at process about 100,000, depending on the size and whatnot, files per hour, which means we can go through several million pretty quickly. One of the things we want to focus on is this idea of variance. One of the things that trips up our current analytical capabilities is the malware writers can make subtle variants in their code, or they can write polymorphic code that'll make the variant.
Yeah, I think they were lethal.
We still have a couple minutes. Oh, really? Yeah, so let's start like a wave. Cheering. The vendors, the developers, the system late, behind the curve. In order to change the arms race, to shift the costs of attack to the other side, or people or money, we need to change the way that we play this game.
All of this is just working from the binaries. We started out thinking, well, we need to disassemble everything and then run our analysis on the disassembled code so we can study the instruction sets and do scalable reverse engineering. And somewhere along the way, somebody said, well, why don't we just try a little experiment taking a different approach. We'll just look at the file, or perhaps sections of the file, like the code section or the data section that has numbers between 0 and 255. And we'll start doing statistical studies on those numbers without really looking at the more anthropocentric view of how we as humans like to read code. So we did that first with just some clustering experiments, and we found that if we combine that with other types of techniques, feature extraction, we could get pretty good clusters out of it. And once we realized that, then we were sort of off and running down this path where we are applying a similar technique.
And I think that this work that David Giametta and Andrew Potter are doing is vitally important to shifting this, the cost of things, to how the arms race is played. And I really look forward to hearing them talk about it. So may I introduce David Giametta and Andrew Potter.
I'm Andrew Potter of the Giametta Potter team up here. So, you just hit. Yeah, got it. Okay. So, what we've been doing for the past 2 or 3 years or so is we've been trying to deal with the question of what do you do if you've got millions of pieces of malware and you want to know, well, what is it that you've got? We started out with only a couple of dozen pieces of malware to work with, and that made it tough, but over time we were able to increase that, and so now we've got a little over 2 million to work with, plus